Hi everyone, I'm Varun Ramanathan from TIFR Mumbai, and today I'm going to talk about some of the ideas behind a recent work. This was joint work with Somnath and Shubhangi from University of Toronto and Mrinal and Ramprasad from TIFR. So what is this talk about? It's going to be about polynomials, their factors, and how we compute them. Polynomials show up everywhere in theoretical CS, complexity theory, pseudo-randomness, coding theory, and the rest of mathematics. Moreover, factorization is an extremely natural operation which shows up even in grade school, and it shows up in a lot of these applications. So it makes sense to try and understand these objects and this operation. The main theorem for today is the following. There is a deterministic algorithm whose input is a constant depth circuit for a multivariate polynomial, and the output is an unbounded depth poly-sized circuit for each irreducible factor of the input polynomial. And the running time of this deterministic algorithm will be the same as the running time of deterministic PIT algorithms for constant depth circuits, which turns out to be subexponential time. Let's try and unpack these terms. We won't see the exact algorithm today, but we'll try and see some of the ideas behind the correctness of this algorithm. Some quick basics. What is an arithmetic circuit? It is the following algebraic analog of Boolean circuits. So it's a directed acyclic graph with addition and multiplication gates, and each output can also be scaled using field constants. It computes polynomials in the natural way in a bottom-up fashion. The depth of any such arithmetic circuit is the longest root to leaf path, and the size of any such arithmetic circuit is the number of wires in this circuit. An important problem that shows up when you start thinking about arithmetic circuits is that of polynomial identity testing, wherein you're given two arithmetic circuits and you'd like to test if they compute the same polynomial. An equivalent way of phrasing this is that you are given a single circuit and you'd like to test if it computes the identically zero polynomial. A sort of easy randomized algorithm for this problem comes from the following principle, which is that a non-zero polynomial cannot be zero on too many points. And a way to formalize this is via the polynomial identity lemma, which is attributed to many people, amongst them commonly Schwartz and Zippel. It says that a non-zero polynomial, when evaluated on a large enough grid, cannot be zero on too many points. And so the easy randomized algorithm is to just pick a large enough grid and sample a few random points and test your polynomial identity on these points. When you start trying to think about deterministic algorithms, a natural definition is that of a hitting set. So a hitting set is some subset of your space of points with the following property. If you care about a subclass of polynomials, script C, then H is a hitting set for C if whenever you pick up a non-zero polynomial in C, there must exist some point in H where this polynomial evaluates to non-zero. So in some sense, it certifies each non-zero polynomial in the class of polynomials that you care about. And if the class of polynomials you care about is, let's say, all degree D polynomials with n variables, then a naive hitting set, because of Schwartz-Zippel lemma, is all the points in a large enough grid. And one of the goals of algebraic complexity theory is to find smaller hitting sets for structured classes of polynomials. A different way of formalizing deterministic PIT algorithms is via a hitting set generator, which is essentially a gadget to reduce the number of variables while preserving the non-zeroness of polynomials in the class that you care about. So it takes a few variables and expands them using polynomial maps into many variables, so that whenever you compose this gadget with any polynomial, non-zero polynomial that you care about, it remains non-zero. And this is useful for deterministic PIT algorithms because now that you're in the low V-rate regime, you can use a naive heating set here, which gives you savings when you're talking about structured classes of polynomials. Alright, so we've talked about PIT and what it means to de-randomize PIT. You'll remember that the main theorem was for constant depth circuits. Why do we care about such circuits? Constant depth circuits are quite interesting, but the reason they are interesting for us is the following breakthrough lower bound against them. So this was a result of Nutan Limai, Shrikant Srinivasan and Sebastian Tavanas, which showed that iterated matrix multiplication, which is an extremely natural problem in algebraic complexity, this problem requires super polynomial sized constant depth circuits. Alright, we are trying to solve an algorithmic problem, and here is a statement which says that you cannot do something, but this is still quite interesting for us because of the following connection from hardness to de-randomization. So Nissan and Wigderson in their landmark paper Hardness versus Randomness showed that you can use explicit hard functions to construct explicit pseudo-random generators. Similarly, Carbonates and Impagliazzo in their algebraic hardness versus randomness paper showed that you can use explicit hard polynomials to construct explicit heating set generators. And when you take this result of Carbonates Impagliazzo and use another structural result of Chow, Kumar and Solomon along with the lower bounds of Limai, Srinivasan and Tavanas, you get the following unconditional explicit heating set generator for constant depth circuits. The important point to note is that the stretch in this heating set generator is from n to the epsilon variables to n variables. And when you do the math, you finally get a sub-exponential time PIT algorithm for constant depth circuits. And this is the reason that the runtime of our factorization algorithm is also sub-exponential. We will refer to this heating set generator as the Ki CKS LST heating set generator. Now let's move on to see some of the main ideas behind the algorithm. And to illustrate these ideas, we will just show two simple applications. One is a PIT application and the second is irreducibility testing. So let's think about this PIT problem. Suppose f is some non-zero polynomial with a constant depth circuit, and now what you're given access to is a circuit for G where you're told that G is a root of the constant depth circuit f. That is, if you take f of x comma y and plug in gx in the place of y, then you'll get the identically zero polynomial. So in that sense, G is a root of f. So the question is, can we do PIT for such a polynomial, which is the root of a constant depth circuit? So remember that the heating set generator we saw, it helps you do PIT for constant depth circuits, but what about roots of constant depth circuits? A natural question here is, does this root have a constant depth circuit? And for now, let us say we don't know whether it has a constant depth circuit or not. The main observation here is that if G is a root of a constant depth circuit, then even without a constant depth guarantee on G, we can still use the Carbonates Impagliazzo plus LST plus CKS heating set generator to test or preserve the non-zeroness of Gx. So note that this heating set generator is only supposed to work for constant depth circuits, but even without a constant depth guarantee on this root, you can still show that it works. And a very quick sketch of some of the proof ideas is the following. The structural result from CKS that is useful is that if f is a constant depth circuit, then even low degree components of any root of this circuit will have constant depth circuits. So it does not say that any root will also have constant depth circuits. It says that the low degree components of any root will also have constant depth circuits. Further, you can extend these ideas to show that any low degree root of this root Gx will also have constant depth circuits. Now finally, by way of contradiction, if the specified generator did not work to preserve the non-zeroness of this root gx, then by the usual Carbonet-Simpagliazzo hybrid argument, you can show that the hard polynomial from LST would end up being a root of this polynomial gx. But the hard polynomial in LST has low degree, and the extension of CKS tells us that being a low degree root of gx, it should also have a small constant depth circuit. But notice that this was the hard polynomial for constant depth circuits, and now we are saying that it should have a small constant depth circuit. This is a contradiction. Hence, the generator must have worked in preserving the non-zeroness of gx. That was a slightly rushed proof sketch, but those are the ideas. Let's move on to the second application, which is irreducibility testing. And the goal is simple. We care about maintaining irreducibility of constant depth circuits. We'd like to find some variable reduction map, just like a heating set generator. We'd like to find some variable reduction map which maintains the irreducibility of constant depth circuits. And you can think of it as, we know how to do irreducibility testing in the low variate regime, and now we'd like to extend it to the high variate regime by using some variable reduction map which maintains irreducibility. And it turns out that using the ideas that follow, you can also extend it to a complete algorithm for factorization. And what's the main idea? The main idea is a bunch of reductions. You reduce irreducibility preservation to divisibility preservation, which in turn reduces to non-zeroness preservation, which is the same as heating set generators or PIT. So to reduce irreducibility to divisibility, consider the polynomial f with a special variable y. The way usual factorization algorithms work is you, after a bunch of cleanup operations, you set the x variables to 0, look at the roots of the univariate f0, y, and then lift them to approximate roots of the original polynomial using either Hensel lifting or Newton iteration. So what do you have? You have a bunch of approximate polynomial roots for your input polynomial. Now, you can show that every potential factor of f must show up via a subset of these approximate roots. So if you take any combination of these approximate roots, that must be a potential factor, if at all there are any factors. The main observation thus is that your input polynomial f is irreducible if and only if none of these potential factors ends up being an actual factor. So if you can maintain this divisibility condition, wherein the potential factors do not divide f, then you can also preserve the irreducibility of f. Now, how do you preserve divisibility using PIT? Suppose G and F are the arithmetic circuits you're given, and you're told that G does not divide F. Now, how do you ensure that G does not divide F even after a variable reduction? The idea is to somehow compute something like a remainder of F and G, and then use the heating set generator to preserve the non-zeroness of the remainder. And the way FOCS did this is by computing a candidate quotient, and once you have a candidate quotient, then you can look at the remainder f minus the quotient times G, and then you can use a heating set generator to preserve the non-zeroness of this term. So what does the candidate quotient look like? In some sense, we are trying to get a handle on f divided by G. So you can try and look at an approximation of 1 by G in the polynomial world. And a very natural way to do this is by looking at a truncated Taylor expansion of 1 by G. And you need to be careful about this because a Taylor expansion might not work. But once you set things right, the main observation to prove here is that G divides F if and only if F minus the pseudo quotient or the candidate quotient times G is equal to 0. So if you can preserve the non-zeroness of f minus q times g, then you can preserve the divisibility or the non-divisibility of g and f. So a quick summary and some takeaways. So we saw that there is a deterministic algorithm which factorizes constant depth circuits and runs in the same time as PIT. Further, the output of this algorithm is unbounded depth poly-sized arithmetic circuits. The first idea we saw was that a specific hitting set generator can be shown to work even for roots of constant depth circuits wherein we had no depth guarantees on the root. The second idea we saw was that irreducibility preservation can be reduced to divisibility preservation, which in turn can be reduced to non-zeroness preservation or PIT. In a sequel, in a bunch of works that we did after this paper, we show that factors of constant depth circuits, factors as well as roots of constant depth circuits do have constant depth circuits themselves. And this uses a version of Lagrange inversion formulas from the 18th century. As a consequence of this structural result, we end up getting a simpler analysis for the algorithm, and we end up getting stronger guarantees wherein we can show that the deterministic algorithm outputs constant depth circuits for each of the factors. And we also get a bunch of other cool applications, and I would encourage the viewer to check out all these papers via my webpage. Thank you.